This paper presents a novel approach to simulate fracture growth in materials using a combined peridynamic and partition of unity method. The proposed method leverages the compatibility of classical material models and peridynamic theory, allowing for efficient simulation of fracture growth in materials. The approach is based on a hierarchical coupling technique, where the partition of unity method is used to solve the equations of linear elasticity globally, while the peridynamic theory is applied locally to simulate fracture growth. The partition of unity method, as described in 1114, is a domain decomposition technique that uses local approximation spaces attached to partition of unity functions to cover the computational domain. These functions, along with their respective local spaces, are used in the Galerkin method to discretize partial differential equations. In this work, the local spaces consist of polynomial functions and problem-specific enrichment functions, which capture local characteristics of the solution. The peridynamic theory, introduced in 1617, is a non-local generalization of classical continuum mechanics that allows for discontinuous displacement fields. It has been widely used to simulate growing cracks and fractures and has been validated against experimental data. 18. The equation of motion in peridynamics is given by 5, where the pairwise force density F encodes the PD material model. This paper utilizes the bond-based softening model presented in 1920, which uses a piecewise constant influence function and a double well potential to define the pairwise force density. The combined PD-PUM simulator is validated against 3 experiments, demonstrating good agreement between experimental and simulation data when using an adaptive strategy for choosing the PD subdomain. This adaptive strategy allows the PD subdomain to move with the crack tip and adapt its size accordingly, leading to more accurate crack paths than using fixed PD subdomains. The proposed method sidesteps the surface effects associated with non-scaled standard peridynamic formulations, making it an attractive alternative for simulating fracture growth in materials. The paper presents a novel approach to simulate dynamic fracture mechanics using a combined PUM-PD simulator. This hierarchical coupling technique combines the partition of unity method, PUM, with peridynamics, PD, to simulate crack growth in a 3-point bending experiment. The approach involves solving the global linear elasticity problem with PUM to provide boundary data for the local PD problem, which is then solved to update the crack path. The crack path is modeled using standard crack enrichments in the global PUM simulation, and the process is repeated at certain load steps. The paper discusses 3 cases of the experiment, with different initial crack lengths and positions. For case I, the authors compare their results with experimental data and simulations from a previous study, 23. They find that the simulated crack path using a smaller, moving PD region is in good agreement with the experimental data at the beginning but diverges slightly over time. The crack tip position also differs from the experimental data at the end of the simulation. In case 2, the authors present a detailed sketch of the combined PUM-PD simulator, showcasing the displacement magnitude of the global PUM simulation, the PD region, and the damage in the PD nodes. They compare their simulated crack path with experimental data and the results from 23. While the simulated crack path aligns with the experimental data initially, it diverges later in the simulation. The crack tip reaches the void at a different position compared to the experimental data. The authors note that they use a similar nodal spacing as in 23, but with a smaller PD region. The paper concludes that the combined PUM-PD simulator shows promising results for simulating dynamic fracture mechanics, particularly in the early stages of crack growth. However, the authors acknowledge limitations in the current approach, such as the need for more robust crack path identification and synchronization of boundary data exchange between the PUM and PD models. Future work includes investigating these issues and applying the method to dynamic simulations. In the context of a study on crack propagation in materials, this research presents a novel approach to simulate crack paths using a moving phase field damage model within a multiscale framework. The approach is compared with experimental results and another finite element phase field damage model, FEMPD, for validation. The paper discusses 3 different cases, each with varying numbers of holes and dimensions. The first case, case I, has no holes, an initial crack length of 1 meter, and a beam width of 6 meters. The experimentally obtained crack path is compared to the simulated crack path using both the FEMPD and the proposed multiscale approach. The results show that the proposed approach closely follows the experimental crack path, while the FEMPD approach deviates slightly from the experimental path. The second case, case 2, involves 3 holes, an initial crack length of 1 meter, and a beam width of 6 meters. The experimental crack path is again compared to the simulated paths from the FEMPD and multiscale approaches. Both simulation methods produce comparable results to the experiment, with the multiscale approach demonstrating a more accurate representation of the crack path, particularly at the intersection with the holes. The third case, case 3, features an initial crack length of 1 meter, a beam width of 6 meters, and no holes. The experimental crack path is compared to the FEMPD and multiscale simulated paths. The multiscale approach better captures the experimental crack path, especially when the crack interacts with a void. The paper also presents a detailed explanation of the methodology employed in the multiscale approach, including the exchange of information between the global and local problems. The phase field damage model is used to simulate the crack growth in the local problem, and the displacement field from the global problem is used as boundary conditions for the local problem. This process is repeated until the crack ceases to advance. In conclusion, the proposed multiscale approach effectively simulates crack paths in materials with varying numbers of holes and dimensions, demonstrating a high degree of accuracy when compared to experimental results and the FEMPD model. The paper highlights the importance of adjusting the frequency of information exchange between the global and local problems based on the specific characteristics of the crack and its proximity to voids or domain boundaries. In the realm of fracture mechanics, peridynamics is a suitable method for naturally developing and growing cracks. However, it comes with high computational costs. This paper presents a combined PUMPD simulator that integrates the partition of unity method with peridynamics to leverage the strengths of both approaches. The authors validate this approach against experimental data from Ingrafia and Gregoriou, 1990, comparing their results to those obtained by coupling peridynamics with the finite element method as in Ni et al., 2019. The proposed method demonstrates good agreement with the experimental data and comparable results to the PDFEM coupling approach. The paper begins by outlining the limitations of current fracture mechanics methods, highlighting the need for a combined approach that can effectively model both local and non-local problems. The authors then detail the implementation of their proposed PUMPD simulator, which utilizes the ParaPX code and the Puma software framework for rapid enriched simulation application development. The validation process involves comparing the simulated crack paths with experimental data for 3 different cases. For case 3, the experimental setup consists of a rectangular beam with 3 holes, where the initial crack is closer to one of the voids. The results show that the PUMPD simulator produces a very similar crack path to the PDFEM coupling approach, albeit with reduced computational time due to the smaller moving PD region employed. The paper also discusses the need for further automation in identifying the PD region, extracting the crack path from the PD damage field, and managing the interaction between the PUM and PD codes. Moreover, it emphasizes the importance of developing 3-dimensional simulations and validating peridynamics models against benchmark experiments. This research paper explores the application of a novel computational framework for simulating fracture in brittle materials using a combination of peridynamics and adaptive finite elements. The proposed method leverages the strengths of both peridynamics and adaptive finite elements to accurately model crack growth and propagation in complex geometries. The paper also discusses the validation of this multiscale fracture model through experimental data, demonstrating its efficacy in predicting real-world fracture behavior. The authors begin by discussing the limitations of traditional finite element methods for modeling fracture, particularly their inability to handle crack propagation without remeshing. They then introduce peridynamics as a promising alternative, which can simulate fracture without the need for explicit tracking of cracks. However, peridynamics has its own limitations, such as high computational costs and difficulties in modeling complex geometries. To address these challenges, the authors propose a hybrid approach that combines peridynamics with adaptive finite elements. This allows for efficient simulation of crack growth and propagation while maintaining the accuracy of peridynamics in modeling complex geometries. The paper provides a detailed description of the mathematical formulation of this hybrid model, including the use of phase field methods to regularize the fracture energy functional. The authors also discuss the implementation of this model using various computational tools, including the open-source finite element library Diehl and the high-performance computing library HPX. They highlight the importance of parallel processing in reducing computational time and improving the scalability of the simulation. The validation of the proposed model is achieved by comparing simulation results with experimental data from various studies on brittle fracture. The paper demonstrates that the hybrid approach can accurately predict crack growth patterns and fracture toughness, outperforming traditional finite element methods. In conclusion, this research presents a novel computational framework for simulating fracture in brittle materials using a combination of peridynamics and adaptive finite elements. The proposed hybrid model offers a promising solution to the challenges posed by traditional finite element methods and peridynamics, providing an efficient and accurate means of modeling complex fracture phenomena.